In this video series, we will treat the complexities of chemical reaction engineering for complex reactions. First, we have to define what is a complex reaction. Then we will go through the algebra, matrix algebra, and the differential calculus of the analysis. Now, let me first write the reaction stoichiometry for methanol synthesis. Methanol synthesis, one of the reactions that define methanol synthesis is using syngas in a 2-to-1 stoichiometry to produce methanol. This is a very common reaction in chemical process industries. It is the largest scale, largest volume of chemical that is manufactured. One of the largest volume of the chemicals that is manufactured as commodity chemicals. We said that we start with a syngas. Syngas is a mixture of carbon monoxide and hydrogen. However, we have a carbon dioxide hydrogen reaction that accompany the methanol synthesis, and we form carbon monoxide and steam. And this reaction is known as a reverse water-gas shift. Water-gas shift, since it is reverse, it is the reverse water-gas shift. Now, when we add those two reactions up, the net reaction becomes carbon dioxide plus 3 hydrogens producing CH3OH plus H2O. Now you see, I generated the third reaction by adding the first two reactions together. So in a reaction network, only either two of those three are independent. The third one is obtained either through addition or subtraction of the two of them. So, independence of a reaction network is important when we are dealing with a complex reaction network. So, we have to make sure that they are independent. In a complex reaction network, there are issues that we term selectivity. That we term as selectivity. Selectivity means the selective production of one of the products in competition to the others. What should we do? How should we design our reactors to improve the selectivity? What type of reactor should we use? Should we use only one or more than one? What are the process parameters? And many more questions, but let us address them first. The independence question is easily answered by looking at the reaction network for a three-reaction system, we can see that only two of them are independent, as we mentioned earlier. The third one is derived based on the two. But if we are dealing with a large network of reactions, we have to use advanced tools of mathematics. The best tool to use, the most convenient tool to use, is to go to a software. In this course, I recommend using MATLAB to determine the rank of a tensor. All right, so I'm recommending MATLAB, which is a shorthand for Matrix Laboratory. And we are going to generate matrices of reaction stoichiometries, and we will base our designs on those matrices. So when we generate the stoichiometry matrix, we can check whether the rank of that matrix is consistent with the number of independent reactions. If the rank is less than the number of reactions that we wrote, obviously some of the reactions are derived reactions that can be derived by the addition or subtraction of some of the reactions that are present in the network. Now let us start generating our matrix, but let us first write this reaction network with simplified symbolic identifiers. And let's write these reactions in a more formal structure. So our reaction 1 is A plus 2B producing C, and D plus B producing A plus E. I selected the first two reactions. These reactions in algebraic notation can be written as minus A minus 2B plus C to be equal to 0. This can be written as minus D minus B plus A plus E equals 0. We can also write this as a summation nu ij times ai equals 0. The first I refers to the species. The J refers to reaction. So we have two reactions. We can write this as nu 1 1 A1 plus nu 2 1 A2 plus nu 3 1 A3. We have three components in this first reaction is equal to 0. Nu 1 1 is the stoichiometric coefficient of the first component in the first reaction. It is minus 1. So this is minus A1, component 1, nu 2 1, component 2 stoichiometric coefficient in the first reaction. This is minus 2. A2. A2 is B now, right? Plus nu 3, 1. It is C. Its stoichiometric coefficient is 1. A3 equals 0. We can also write the second reaction in the same format. Now our reaction index is 2. This is reaction 2. Again, the same definition, general definition is valid. We are going to use different indices. Nu 2, 1. Component 1 was A. Nu 2, 1 is plus 1. A1, this is plus 1. Nu 2, 2 component 2 is B. B has minus 1 as the reaction stoichiometry, A2. Nu 2, 3, the third component is C, and we don't have it here. Let's just put it 0 times A3. Nu 2, nu 1, 2, I'm sorry, nu 1, 2, nu 2, 2, nu 3, 2, plus nu 4, 2. Nu 4, 2, our fourth component is A, B, C, D, minus 1, A4. Our fifth component is E, plus A5, nu 4, 5, 2. Nu 5, 2 is equal to 0. So now we have matrix-friendly components, matrix-friendly stoichiometric coefficients. Now we are going to generate our matrix. Let's do that. So our reaction matrix is going to be nu ij, A1, which is A, A2, which is B, A3, which is C, A4, which is D, A5, which is E. So we have reaction 1 and reaction 2 here. And you will understand why I wrote it in this fashion. All right, A1, minus 1. A2, minus 2. A3, plus 1. A4, 0. A5, 0. The second reaction, A1 is plus 1. A2 is minus 1. A3 is 0. A4 is minus 1. And A5 is plus 1. Okay? So we have generated our nu ij matrix or nu ij tensor. So we have component vector. This row is the component vector, and this column is the reaction vector. Reaction 1, reaction 2, and so on and so forth. Now let us do the matrix multiplication of R1, R2 with this stoichiometric coefficient matrix. I will derive the first component. R1 multiplied by -1 minus R1, R2 multiplied by 1 plus R2. This is my first term. Let me just do a little bit of housekeeping. Okay, so my first term, I'm going to generate a vector space. My first term is minus R1 plus R2. This is my first term. This first term belongs to the A column. My second term is minus 2R1 minus R2. This belongs to the B column. My third term is R1 only. This belongs to the C column. My fourth term is minus R2. This belongs to the D column. And my fifth term is plus R2. This belongs to the E column. Now, when I did this matrix multiplication, what I generated was the net rate of reaction with respect to that component. This indeed R sub A. This is R sub B. This is R sub C. This is R sub D. And R sub E. Once we have a reaction network of independent reactions, we can establish the reaction stoichiometry matrix. We can have their independent rates of those reactions, and the matrix multiplication in this fashion gives us the rates of reactions with respect to that particular component. So this R1s and R2s are in the following form. R1 is equal to K1 times Ci to the power alpha I. And R2 is in the form of K2 pi summation over all species Ci to the beta I. And when I do that, I mean something like this. This is K1, Ca to the alpha 1, Cb to the alpha 2, and so on and so forth. We don't know alphas. We don't know whether those reactions are elementary. We don't know if there are other elementary independent steps that are hidden underneath that overall reaction layer. Similarly, this is K2, Ca to the beta 1, Cb to the beta 2, and so on and so forth. So when we are dealing with such complex situations, it is easy, it is better to simplify them in broad contexts as multiplication operators, in summation operators, in clean and clear indexes, and represent them in matrix form as such. So once those rates in terms of RA, RB, RC, RD, and RE are rigorously written, independently defined, the engineering part will be easier to handle. In this video, we are going to derive the design equation for a batch reactor for a complex reaction network. So our reaction network is going to continue to be the methanol synthesis reaction. We are going to first write the design equation for a batch reactor for a simple reaction, and then we will see how we can add the complexities into it, and then how we are going to use the tensor algebra to simplify the expression. So the design equation for a batch reactor for a simple reaction was dNA over dt to be equal to R sub A times V. Now we have, instead of R sub A, B, C, we have R1, 2. Now remember, during the matrix multiplication, we said that R1 multiplied by A1, this first term, stoichiometric coefficient of A1, all right? So this is nu 1, 1. R1 multiplied by nu 1, 1. Let's apply that logic here. RA is equal to nu A times R times V. This is the more rigorous representation of reaction rate. Now, in a complex scheme, we should be writing this. So let's simple reactions. We should be writing this for complex reactions as dNA over dt to be equal to summation nu A J times R J times V. So we are summing overall the reactions. It is this vector that I'm talking about, right? Nu AJ times RJ is equal to RA. This whole term is equal to RA. So this is for the complex reactions. Now let's take this term, treat it for a constant volume reactor. Remember, when the volume was constant, we were able to bring it into the derivative to write dCA over dt to be equal to summation of nu A J times R J. So this was our row vector. This is our tensor. We have another vector actually. We have a column vector of components. A, B, C, D, E, F components. So let us write those column vector as a vector AI d over dt. Let's generate our symbolism. dAI, A1, 2, 3, 4, 5 is equal to, now I'm going to save time, space, and I'm going to write the stoichiometry matrix as a tensor. And this is a vector when I just throw underneath. When I do double, it's a tensor. Vij times Rj times V. So AI refers to Ni, number of moles within the system boundary. This is also a vector, all right? I cannot write in boldface on the board, so I have to use a symbolism that reflects that this is a vector. One line underneath represents a vector, two lines represent a two-dimensional vector, which is a tensor. So this is the most general representation of the design equation in vector notation or in tensor notation. In this video, we will learn the performance indicators of a complex reaction network. The performance indicator of a single reaction was conversion. Conversion is an indicator if we are dealing with a simple system in a single reactor. Still, we can estimate the conversion in a complex reaction system as well, but our indicator is not going to reflect the conversion in each of those reactions. Conversion is an indicator for a reactor, but not for the individual reactions that are taking place in the reactor. When we have more than one reaction, we have to also identify in which proportion these reactions went towards production and how much of the feed is used to produce our desired product. So we have to define the terms such as desired and undesired product. The desired product in this reaction network is methanol. And the undesired product is water. It is consuming our useful reactant, which is hydrogen. Okay? So, the conversion can be defined for the principal reactant. If we look at the net reaction, or if we have chosen to write this reaction in terms of carbon dioxide, we could have said defined conversion for carbon dioxide. In this case, we can write the conversion for carbon monoxide or hydrogen. Let us write it for hydrogen. All right, it is involved in both of those reactions. So instead of CA0, we can write CB0. I'm going to skip the symbolism, but I will define the selectivity and the yield. Selectivity can be defined in terms of overall selectivity and instantaneous selectivity. And why we define as overall and instantaneous selectivity will become more relevant when we are solving problems in a plug flow reactor or in a mixed flow reactor. Selectivity is the amount of desired product formed per reactant reacted. So let me correct the conversion in our particular reaction for B, because it is our principal reactant in this reaction network. Selectivity is the relative amount of desired to undesired product. So C minus C0, how much of C formed per mole of CE minus CE0. If we are measuring concentrations, if we are measuring number of moles, we can define selectivity as NC minus NC0 for a batch reactor divided by NE minus NE0, or we can define that as the molar fluxes FC minus FC0 divided by FE minus FE0. So these are overall selectivities. I measure the amount produced at the end of the reaction, compare it to the amount that I have put into the reactor in the beginning, and so this gives me the overall selectivity. This is the overall selectivity. Then we define the instantaneous selectivity, and it is related to the rates. R D over R U, the rate of the desired reaction to the rate of the undesired reaction. This is the instantaneous selectivity. We have to define one more term. We have defined conversion. We have defined selectivity. We have to define the yield of the reaction. Yield gives us how much of the reactants that are converted are used to produce the desired product. So it is, in mathematical form, it's conversion times the selectivity, or it is the desired product C minus C0 divided by CA0 minus CA. So much is converted. So much is converted. How much of this is used to produce the desired product? So these are the performance indicators of a complex reactor operation. We will use conversion, selectivity, and yield, and we will optimize our design, choosing, for example, conversion as our key performance indicator. We're choosing selectivity as our key performance indicator, and we will optimize the reactor operation, design and operation for that. In this video, we are going to learn or remember the reaction concept of reaction extent. It is a performance indicator, but it is going to be used instead of a familiar concept of conversion. So we have more than one reaction, R1 and R2. In the top row, I wrote the reaction rates, the stoichiometry matrix, and reaction rates for individual components as we have written already. And the transpose of this is sometimes more convenient. In the second row, we have the transport stoichiometry matrix or tensor. Then, of course, the reaction network has to go to the other side of the matrix, and we have the column vector of reaction rates of the individual components. So we are carrying out this analysis for a batch reactor. Here is our design equation for a batch reactor. dNA over dt is equal to Ra times V, and I'm going to integrate this expression between the initial and Na minus Na0 I would like to have a common function that is going to represent that particular reaction. So instead of Ra, I'm going to write R times nu Ai and integrate with respect to time. And this should be equal to an extent of the reaction psi 1 summation over all the extents of the reactions that are involved, that involve component A. So extent of reaction is the term that defines how many moles of component A is produced from reaction 1, how many moles of component A is produced from reaction 2, or vice versa, consumed. So this is going to be a strong function of the reaction stoichiometry, just like the reaction rate. So we are removing the rate concept and generating an algebraic equation by simply relieving the derivatives from the batch reactor analysis. And this is going to be useful also when we are performing a CSTR analysis. Let us discuss these concepts with an example of a complex reaction network, 2A plus 3B going to R, B plus D going to S. R1 is given as K1 Ca times Cb, and it is represented by Xi1, and R2 is K2CbCd, and it is represented by Xi2. So Xi1, just to be sure, it has the units of moles. This has the units of moles, while R1 has the units of mole per volume per time. So let us write the overall balance equations. Na0 minus Na, how much A is consumed, is going to be 2 Xi1 and B0 minus NB will be 3 Xi1 plus Xi2, 3 Xi1 plus Xi2, and D0 minus ND is Xi2 only. And let's write for the products also. And R0 minus NR is minus Xi1, because it's on the product side, and S0 minus NS is equal to Xi2. Now let's take the derivative of each and every one of those to express all of the species number of moles in terms of only two parameters. dNA over dt will be equal to minus 2 d Xi1 over dt. dNB over dt will be equal to minus 3 d Xi1 over dt minus d Xi2 over dt. dND over dt will be minus d Xi2 over dt. Now, as you see, we are reducing a 5-dimensional space into a 2-dimensional space, Xi1 and Xi2. In a single reaction network, we were using conversion to bring a multidimensional component space into a one-dimensional conversion space. Here, in a complex reaction network, we are converting a multidimensional component space into the space that is defined by the reaction extents. So let us write the derivatives here as well. dNR over dt is going to be the Xi1 over dt, and a dNs over dt will be equal to d Xi2 over dt. Now we are going to introduce the design equation. Instead of dNA or dNR, we're going to write the reaction rate with respect to R. So this is going to be R times V, right? R times V. What is R? It is R1 times nu R, that is equal to R1 times V. This is going to be R2 times V. And we are going to introduce concentrations, the rates in terms of concentrations, K1 times Ca. Ca is Na over V. Let's make sure that we have the note here that this is a constant volume reactor. Okay, K1, I will write Ca times Cb times V. Ca is Na over V. Cb is Nb over V. And Na and Nb are expressed in terms of reaction extents. We're going to substitute for those as well. Let's write for S for the completeness. This is K2 times Cb Cd times V, and this is Nb over V, and this is Nd over V to be substituted. Using our cleaned up version of our board, let us define Na, Nb, and Nd in terms of psi1 and psi2. Na is equal to Na0 minus 2 psi1. Nb is equal to Nb0 minus 3 psi1 minus psi2. Nd is equal to Nd0 minus psi2. So I'm going to substitute this into these differential equation. D psi1 over dt is equal to K1 Na, Na0 minus 2 psi1 times Nb, Nb0 minus 3 psi1 minus psi2 times V divided by V square. V's cancel, and I'm left with only one V. We have d psi2 over dt. We're going to substitute these terms. K2 times Nb, Nb0 minus 3 psi1 minus psi2 times Nd, and d0 minus psi 2 divided by v square multiplied by v divided by v. Volume is constant. So I have two coupled ordinary differential equations to solve with the initial conditions. At time t is equal to 0, psi 1 is equal to 0, psi 2 is equal to 0. Solution of those coupled ordinary differential equations are not trivial. It will require numerical tools, and I refer you to numerical tools such as MathCAD, MATLAB, or Polymath to solve this set of equations. Of course, when numerically solving these equations, we will need numerical values for NA0 and B0 and also the other constants. But once we have psi 1 and psi 2, we can solve for all the other concentrations such as A, B, C, as well as R and S.